Welcome back. Now we get to an example for interference of waves, of sound waves. We have a speaker at the position -30, we'll call that speaker 1, and then speaker 2 at the position 20 on the x-axis. And then the wavelength of the sound wave is given as a 0.4 meters. And then we have some questions that we can ask of this. It says, where along the x-axis is there constructive and destructive interference? So where is going to be the points of constructive interference along the x-axis? B, where along the y-axis is there constructive and destructive interference? And then where along the line y equals to 4? In other words, a position here 4 meters up from the x-axis. Where along that line is there constructive and destructive interference? And then we can ask various questions like that of these kinds of questions. In the midpoint, somewhere here in the middle, there's going to be a point where it's equidistant from both of them, right? And then the waves are going to reach there and they're going to be completely out of phase. So along the x-axis, the midpoint gives the central maximum. We call that the central maximum, right? Because it is equidistant from both of them. So right here, and it's going to be 2.5 meters from speaker 2, and it's going to be 2.5 meters from speaker 1. So that will yield the central maximum, right? What other points will yield constructive interference? Well, let's just say any point here, x0, right? So the distance from here to here, 2 minus x, right? From this point to this point, right? And then that's going to be, we can call this one here R2, then we can call this distance R1, and then R1 is going to be what? X minus -3, x minus -3, right? And then, so the difference of these two distances has to be integer number of wavelengths, right? It's going to be R1 minus R2 is equal to n lambda. If it's integer number of wavelengths, then we're going to get constructive interference, right? X is equal to n lambda, and then we have here 2x plus 1 is equal to n lambda, right? So this is the general case where you will yield a constructive interference. 0, what do we get? If we put n is 0, we get 2x plus 1 is 0, x is equal to -½ So that will give us the central maximum, right? Now let's put n is equal to 1. N is equal to 1, then we get 2x plus 1 is equal to lambda, and then the wavelength is equal to 0.4. That means where? That means -0.5 was here, so let's just say this is 1 meter, 2 meters, 3 meters, right? -0.5 was here. -0.3 is going to be positioned a little bit to the right. So this is going to be the central maximum. And then the n equals 1 maximum is going to be -0.3. Then we can keep doing that, right, until we generalize. That's equal to -0.2, x equals to -0.1. So then you have -0.5, -0.3, -0.1, and then it's going to keep going, right? The next one is going to be all of those until we get to 1.9. They're going to yield constructive interference. Then it's going to be on this side by 0.2s until we get to -3, right? How about on the right side of the speaker 2, and on the left side of the speaker 2? What's going to happen there? Okay, if we're on the right side, somewhere here, the distance from here to here is going to be a certain distance, right? And then the distance from here to here is going to be whatever that distance is plus the difference of the two speakers, right? In other words, no matter how far I am to the right of the speaker 2, the differences in their distances will never change. What is the distance between them? 5 meters, right? Equal to integer number of wavelengths, right? 5 is equal to n, and then this is 0.4. N is equal to 5 over 0.4. So, in other words, on this side of the speaker, you're not going to get integer number of wavelengths. So, no matter where you are on the right side of speaker 2 and on the left side of speaker 1, you never get constructive interference. Why? Because no matter where you are, the difference is 5 meters and it's not equal to an integer number of wavelengths, right? Now let's do the destructive interference on the x-axis, right? So then the differences in their distances is going to be, use the same delta r that we had before, 2x plus 1, and then we can set that equal to n plus a half lambda, right? And then we can try n is equal to 0 right here. 2x plus 1, n is equal to 0 will give 0, and then you get half of 0.4. So you can see that that makes sense. Negative 0.5 was the central maximum on the x-axis. Negative 0.4 is going to be the first minimum, right? First destructive interference. So it's very logical because it's in the middle between the negative 0.5 and the negative 0.3. The other ones we don't even have to do. Then we know the next one is going to be negative 0.2, then the next one is going to be what? 0. So the origin itself, then you're going to have 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, 1.8, and then 2.0. In other words, the speaker itself, right at the speaker, there'll be destructive interference because the difference in their distances is equal to half the integer multiple wavelength. Then it's going to be the same thing on the other side, right? On the either side of the speakers, right? On the other side of the speakers, the differences in their distance was always 5 meters, right? So what does that mean? Well, no matter where I stand on the right side of speaker 2 and on the left side of speaker 1, I get complete destructive interference. The differences in their distances are always equal to half of the wavelength of the wave. Okay, so you get complete destructive interference. This was kind of a coincidence that it happened that this ended up being, the 0.4 ended up being such a specific number that the differences in their distances was always equal to an integer multiple of half their wavelength, right? So now let's do the y-axis. Multiple of the wavelength, right? So if I put n is equal to 0, can I ever achieve n is equal to 0 there? Well, not really, right? Because this distance will always be greater, the r1. So you can't achieve n is 0. How about n is 1? So then you just have 0.4. So then you just have here square root of y squared plus 9 minus square root of y squared plus 4 is equal to 0.4. We can put this into the calculator, into the solver function, and have it calculate this for us. Should make sense. So 5.71 meters up this way and 5.71 meters that way, you get to hear a constructive interference. N is equal to 1. There is no n is 0 on the y-axis, right? So if there's there an n is equal to 2, then we can try here 0.85. So that's kind of interesting. N is equal to 2 came closer. Why? What happened here, right? What happened? Because usually we would think that as you go farther away, then the n value should get larger, right? Why is it that n equals 2 came closer? As you go closer and closer to the x-axis, the difference in their distance is actually getting larger, right? So at 1.85, the difference in their distance is 0.8, right? Now, as I try n is 3, that difference in the distance might not even exist. So let's try here n is 3, and we would get here 1.2. There is no answer. So along the y-axis, there is no n equals 3 constructive interference, right? So now we can do the destructive interference. The only difference is in the destructive interference, it's going to be 1/2 integer multiple of the wavelength, right? So you can kind of see here that the n equals 1 constructive interference was at 5.7 meters, right? But that was when their difference in their distance was 0.4 meters, right? Now when I ask the difference in their distance to be less by half of a wavelength, 0.2 meter, right? Then the point came out farther away, which goes to my earlier point that the farther away you are, the less the difference in their distance is, which is in this case 0.2 meters, right? 12.24 meters. And then negative 12.24 meters are yielding n equals 0 destructive interference. So this is n equals 0 destructive. Now I'm getting closer. So 3.31 would be here. That would be n equals 1 destructive interference. And then this is n equals 1 also. Now we're getting closer. Then we can try n equals to 2. right? So n equals to 2 would be 2.5 wavelengths, right? So that would be 1 meter, right? Well, actually, we knew about that because earlier when we were doing the x-axis, we found out that the origin was destructive interference, right? So this answer matches with that. So it actually makes perfect sense. So we're able to fit n equals to 0 here and here, n equals to 1, and then n equals to 2, and then there is no n equals to 3 along the y-axis, right? Okay, now let's go along this way, along the line y equals to 4. Okay, where will the central maximum be over there? Well, it's kind of like saying the x-axis. The only difference is that we pulled it up now. So the central maximum, n equals to 0, is going to be negative 0.54, right? Earlier we saw that negative 0.5 gives you the central maximum along the x-axis. So all we're doing it is vertically moving it, transitioning it to 4 meters up. So it's just going to be negative 0.54, that's central maximum, right? And then we can do any general point, x4, right? And then we can do the distance equation. If we want to search for n equals to 1 first order constructive interference, so we put here 0.4, then we solve for this meters. And of course, it's 1 to 2 meters and 4 meters this way. So, whereas the constructive interference here on the x-axis was negative 0.5, and then the next constructive interference was negative 0.3, right? But over here, it doesn't work that way. So over here, it's negative 0.122. So it's slightly more over this way. We search for them over here on this side, we just have to switch these two, right? When we switch these two, then it gives us the same answer on the left side. But it's pretty much symmetric. So I'm not gonna do it for now, but all you have to do is just switch them, and then it gives you all these answers, right? So then we put 0.8. Let's see what we get for 0.8. N is equal to 2, right? So that's the difference in their distances is 2 wavelengths. Then I can keep doing that. 1.2, right? So is there any limit to that? Is there a limit like along the x-axis? When we got to the speakers, that was it. On the right and left side, it was complete destructive interference. Well, what's going to happen over here? Is there a constructive over here? Does it just keep going, on and on and on? Well, we could try here any multiple of the wavelength, right? So remember the wavelength was 0.4, right? N times 0.4. Okay, so now we see that you're able to fit all the way, n is equal to 10, and then you're already over here on the two sides of the speakers. On the x-axis, you were able to fit the constructive interference only between the two speakers. On the two right side of the speakers, it was complete destructive interference, right? But now you're able to fit all the way to n equals to 10. Well, what's the next n that you can fit? Well, we can try n is equal to 11, right? 11, and then you're gonna get 4.4 meters. Answer comes out to be 7.23. So it goes all the way. So if n equals 10 is here, n equals to 11 is here, and then this one is equal to 7.23. Right? Can I fit n equals to 12? Let's try n is equal to 12. Right? And then you get here 4.8. And then you get 13.4 meters. N is equal to 12, 13.4 meters, and then 4 meters up, right? So I'm able to get a lot of constructive interferences, and it's outside of the two speakers, right? But then, can I fit n equals to 13? If I put n equals to 13, 13 times 0.4, 5.2. Look what's going to happen if I try 5.2. This one comes out to be no answer, right? Why? Well, the maximum distance between them, between their two distances, cannot be any more than 5, right? They're 5 meters apart. So no matter how far I go to infinity, the difference between the distance from the speaker to that point and this speaker to that point can never be more than 5 meters. So you can't have n equals 13 constructive interference. So that's the last one that you can have. N equals 12. You can fit all the way to n equals 12, and you can fit all the way to n equals 12 on the other side, right? How about destructive interference, right? N equals to 0. So we're just going to put here 0.2, right? So negative 0.311 gives it to us B then. So it's very similar to how it was on the x-axis, right? n equals 0 central maximum, and we have here n equals to 0 first order minimum, then we have n equals 1 maximum, and then so on. So I could keep doing that and then find out all of the minimum values, and then we're going to get to a certain limit, just like we got for the constructive interference, right? What's going to be the limit? Well, if I try n is equal to 12, what's going to happen? Square root of x plus 13 squared plus 16 minus square root of x minus 2 squared plus 16. And then if I try 12, that's 12 and a half times 0.4. There's no answer for 5 meters because the difference in their distances is 5 meters only when you're on the x-axis, right? So you do not get n equals to 12 for destructive interference. The most you get is n equals to 11. So n equals to 11, it'll be 11 and a half. 11 and a half times 0.4. Where does that take us? 9.17. It's going to be between the n equals to 12 and n equals to 11 constructive interference, right? So you'll be able to fit actually more constructive interferences than destructive interferences, right? So you can kind of see how this works, okay? So let's say this is the point negative 0.5, 4. So imagine this was a home theater system. We say, okay, what if there was a speaker in the back here, behind the person? Where should that be placed so that the central maximum stays where it is? So the person can sit in the middle and hear the maximum intensity sound wave from all 3 speakers, right? So we basically want the idea for this to be equidistant, assuming that all speakers are coherent and they all have the same wavelength, right? And they're always in phase with each other. So where would you place this? So the idea behind that is that the distance here needs to be pretty much the same, right? So we can calculate what R1 is, right? And the root of this distance here would be 2.5 and 4, right? So 2.5 squared plus 4 squared. 4.717 meters is the distance between here and here. Now, of course, R2 is the same distance too, 4.717 meters. So basically, you would put the speaker 4.717 meters behind the person, right? So that would be at the point negative 0.5, and then 4 plus 4.717, that would be 8.717 meters, right? So you want to make sure that they're equidistant. Or if you want, you can put 2 speakers that are equidistant, depending on where you want to place them. So as long as they are equidistant, they will all get there in phase, and then the central maximum will stay at the same location, okay? So now you can see how we can analyze different situations like this with 2 sources of sound wave, and how we can find the central maximum, and then other orders of maximum, and how we can find the destructive interferences also, okay? Thank you very much.